From lathes battling stringy chip nightmares to fear-inducing two tools rapiding up to the cut at the same time, this is why lathes are beasts compared to mills. Let's hop in. And I know that we're gonna get a lot of hate piled on from this video, but before that happens, I want you to know I got a lot of love for my mill bros. I started out on CNC Mills. And a little sneak peek, follow along for next week's video. We might, as the kids say, flip the script and maybe talk about it the other way around. But for right now, I'm gonna go over why I think lathes are harder to work on than mills. And when I mean lathes, I don't mean the 2-axis Hardens from 1975 with some old grandpa there turning a little screw down in his garage. I mean a CNC lathe. Twin turret, twin spindle, Y-axis, C-axis, live tooling. Those I think are harder to work on than mills. The first reason I say that is weighting codes. For people out there that don't really know the inner workings of programming a multi-function machine like this with two turrets, we use something called weighting codes. It's where one turret, you can't just have both turrets doing anything willy-nilly at the same time. One turret sometimes waits for the other. Well, most often in every program, one turret waits for the other one to finish. One operation has to finish before the next operation can begin. That's why we use weighting codes. And some programs I've done have 20 or 30 different weighting codes, and they have to be set in the same, they have to be set in the perfect way for your program to be optimized, not only for cycle time, but also for safety. Not safety of the operator, because we're going to keep the door closed while we set up and run, but safety of the machine, safety of the tool, safety of the spindle, the turret, etc., etc. So for instance, say I'm rough boring or boring from my lower turret to the main, but I have to drill first. I cannot drill and bore at the same time. I need to drill comes out, goes home, then I index around to a boring tool. Well, before that bore goes in, I have to make sure my drilled hole is there. And that's a very simple explanation of M codes and weighting codes. The reason it's difficult, if you make a mistake, bam, slap. Now, that doesn't mean the weighting codes themselves are difficult. And I know a lot of that would go on the programmer and the person setting up at the machine ultimately, but they are a challenge. That's first reason. Let's talk about the next. So to expand on the weighting codes and what we talked about in the first section about weighting codes and one tool waiting for the other one to finish, one turn spindle waiting, that leads me to the next hard, difficult thing about a lathe. Two tools in the cut at the same time, like this. That is what we call pucker factor 7,000. It is a heck of a challenge to run that through at 100% rapid, not on single block, two turrets at one time before proving out the program. Which you should always prove out the program. If you write the program and then you go set it up, you already have an upper leg because you know what's going to happen. But if someone else wrote the program and you're running it through, it's a good idea, run that upper turret alone, run that bottom turret alone, then you could run them both together. That there in itself takes such a high level of skill, experience, I would even dare to say stoicism, to run that through repeatedly and not smash, but B, keep a cool level head about it. Some of these machines are lightning fast, and if your instincts and your experience aren't all at top tier for that particular day, you could have one heck of a smash. So what I'm going to show you right now is, oh, and also to compare that to mills, on a mill you have one tool at a time. And I love mills, man. Like I said before, got a lot of love for my mill bros out there. You're not having two tools rapiding 50 thousandths away from each other at the same time 50 thousandths away from the material. So I'm going to show you right now a program that I ran through, and I sped it way up because we don't want to sit there for 3 minutes. But this is one I took a few hours to optimize. We have very little dwell time between either turret. I kept them as busy as you can, but you could see the time that they're overlapping, cutting together. And those are all weighting codes, M90, M90, or M900, 901, 902. The M900s up to M999 are weighting codes for our machines. You'll see it in there, the tools cutting together, weighting codes. This is what it looks like. So you saw that, pretty cool. I really enjoy doing that, optimizing cycle time. But let's move on from that. The third reason I think that lathes are more difficult than mills, chip control. Man, I've made a few videos for practical machinists on optimizing your tooling, your speeds, feeds, what you can do to manage your chip control better. So you can check that out at Practical Machinist to see it. But that's not what we're talking about in this video, how to fix that problem. It is a consistent issue with CNC lathes. Now, one of the reasons it's difficult, more difficult on a lathe versus a mill, is your turret. Your turret can pack up with chips, and in the conveyor it can. We use chip conveyors that take the, right through here, down here, chips go through, come out of conveyor into a thing. Well, our machines, like most CNC machine shops, your lathe is running automatic, unattended. You know, whether or not the operator's at break, setting up another job, checking a part, we're not standing here running one part at a time. We're automatic. So that machine is running, we're walking away. That's a challenge in and of itself. But you can look right here what happened when we walked away and the chip conveyor temporarily took a dump. So as you can see there, the chips were building up in the conveyor because the conveyor was jammed. Also, the turret was getting wrapped up with chips for whatever reason. Maybe the tool wore, coolant direction wasn't correct. I'm not sure really what happened, but we clicked a pic of that from last night. That's a battle on CNC lathes that has been fought since the beginning of time. When cavemen were running CNC lathes, they were trying to figure out how they can better control those chips. I've been on mills off and on for a long time. I've never had a problem with chip buildup anywhere. Now, keep in mind, I haven't run fancy 5-axis with like deep pocketing and stuff like that, but I've never seen a turret get full of chips on a mill. Never had it wrap around to the point where the turret wouldn't even index anymore because it was so packed up. And a lot of you say, well, that's your fault, Luke, and maybe it is. If it is, pin a rose on my nose and call me a donkey. I'll admit that 100% for sure. But no matter whose fault it is, it happens in the world of CNC lathes. Have you ever ran a lathe and it hasn't happened? If so, drop a comment below. Here's one last picture of a Swiss machine, and this is just a little bit of chips building up. I went to a random Swiss, popped a picture. This is what it looked like. Now the last and final section we're going to go over on why I think lathes are more difficult than mills, and when I mean difficult, operating, setup, mainly operation, is our work holding. On a mill, and keep in mind, I'm not talking about the one person with a mill that they're loading a 7,000-pound block of Inconel that they have to indicate and 400 operations and on a $2 million Toshiba. Although, keep in mind, next week we're going to talk about that. But standard run-of-the-day mill. Take a block, throw it in a vise, tighten it down, indicate it, boom. You're done, part's done, hit start, walk away, go home. Just kidding. I know it's a lot more difficult than that. And the mill bros out there, you guys are freaking awesome. But the work holding on lathes is another battle. On a part like this here that we run, our TIR, this is the main side, we transfer, and then we do all this on the sub. Our run out from this ID thread to this OD thread and these features has to be 0.002 maximum. What does that mean to the layperson? It means it's very difficult, and unless you're work holding on your main side, your work holding on your sub side is optimal. Dare I say perfect. You're not gonna hold that. You're not gonna hold 0.002 run out. Maybe one part, but we're talking about that machine is gonna run automatic. 7, 8, 10-hour day shift, 7, 8, 10-hour night shift, running nonstop, repeating that same feature over and over and over on a 4-minute cycle. Machine, sub spindle comes up, grabs it, parts it off, goes back, machine over here, over and over and over. Every 4 minutes it's going to repeat that until the job is done. Some orders we make at 10,000 parts that I'm going to show in just a minute of that work holding. So your main spindle work holding has to be true. Your sub spindle pads themselves, or collet or chuck, has to be bored or made to that exact, the middle of that exact dimension. And then the run out has to be good to that spindle. But there's one last trick. The two run outs together have to be what we call dead nuts. So this is a perfect example of where that run out from main to sub has to be what we call dead nuts. Here's our main side. We machined the part, sticks out about that long, and then our sub spindle moves up and transfers it. It grabs over a round that we turned on the hex, sub closes, cutoff comes, cuts it off, and then sub goes home. If these pads are not nearly perfectly concentric with this turn diameter, the part would undoubtedly be bad, but even worse, the machine could smash up upon transfer. And we have to make it perfect that way. We have a 3-minute cycle time. Every 3 minutes, the sub goes to the main, transfers, goes home and machines over and over for 20 hours a day, Monday through Friday. So not only does it have to be perfect, it has to be within 5/10 run out from sub to main and repeat over and over and over for 10,000 cycles, sometimes even more. That's why the run out on a lathe is so important. So in conclusion, that's why I think lathes are such beasts compared to mills. And as I alluded to a couple times through the video, before everyone piles on and calls me a communist or something like that, wait for Friday. It's going to be a great, great video next Friday. That's all I can say for right now. But lathes are awesome. Mills are awesome. Certain shops don't run any lathes. Certain shops like ours don't run virtually any mills. We have one mill that we don't really use a lot. For me, I'm a lathe guy. That's the way I roll. That's what I do. So of course I'm a little bit biased. There's people on mills that make such awesome stuff, man, and I watch, they're on Instagram, TikTok, YouTube. I watch their stuff. I'm like, man, these people are awesome at their job. It's great to watch, great to learn from them, great to see how they do it. But for me, I think a lathe is harder than a mill. What do you think? Comment down below, good, bad, or ugly. Are you a lathe person, mill? What do you prefer? What do you think is harder? And what's easier or hard about them? Once again, this is Luke with Crusader Machining. I am signing out of this video. Check me out on TikTok and Instagram. Share the video, like it, subscribe, blah, blah, blah. Thank you for watching. Catch next week's video.